Welcome to the Walton Pi. Today we're going to be talking about continuity of functions. So the idea of continuity is very similar to what it is in everyday English. So if something's continuous, there aren't any breaks, jumps, or gaps. So the Mississippi River is a continuous flow all the way from the northern part of the U.S. all the way to the Gulf of Mexico. There aren't any breaks, there's no jumps, like the river doesn't disappear from one spot and reappear somewhere else. That's the sort of idea of continuity. So if you use something continuously, there's a continuous flow of people. All of these are implying that there aren't any breaks and it's just continually there. I used it again. It's just consistently being used and there aren't any weird jumps or changes that are happening. And it's going to be the same thing in mathematics. So the way that we define continuity is a function is continuous at a point A if the limit of the function at the point A is equal to the actual value of the function. So what does it mean for the limit as x approaches a of f of x to be equal to f of a? Well, it's going to mean three different things, and these are the three things that can cause a function to not be continuous. The first thing is we need f of a to exist, meaning there can't be a hole at a. So if there's a hole in our function, it's not continuous there. The next one says that the limit of x as x approaches a of f of a must exist and must be finite. So there aren't going to be any asymptotes, and we're not having the function approaching infinity somewhere in the middle of our function. And then the last one is that the limit as x approaches a of f of x is actually equal to f of a. So that tells us that there isn't a jump from one value to another. So if we were to look at a graph, this graph is demonstrating all three of these different places where we could run into a problem. If we are moving from left to right, the first thing we come across is a hole with the function being equal to something else at that point. So this is a representation of a hole. So the function is if we removed the solid dot above it, then that would just be a graph with a hole, and so the function wouldn't be defined at that point, so it couldn't be continuous there. But even with the point reinserted into the graph, because it's not on the graph, it's not at the same point as where we would expect it, it's not going to be continuous there. Moving on to the second one, where we have the vertical red dotted line, that's representing a vertical asymptote, where the function is approaching infinity there, which tells us that the function is also not going to be continuous at that point. And then the last one is a jump, where it's going from a fairly low value jumping up to a higher one. That's going to be a jump, so the limit does not exist at that point, which tells us that we can't have the function be continuous there either. We can also tweak our definition to have continuity on the left and the right. So if we were to go back to this image, if we're looking at the very last discontinuity, the one at the very, very far right, if we look at that function, it's going to be continuous from the right, because if we approach that jump from the right-hand side, it's going to approach the value that it at that point. So it's continuous from the right there, but it is not continuous from the left, because from the left-hand side, it does not approach the actual value. And so this is just what continuity from the left and continuity from the right means. It means if you look at the one-sided limit and it's equal to the value of the function there, then it's going to be continuous from that side. We can also talk about continuity on an interval. So this is just saying that a function is continuous on an interval if for every single point in that interval, f is continuous at that point. So we just have to check each point inside. If f is defined at one or both endpoints, we're just going to use the one-sided definition of continuity. There's also a few theorems with continuity. So if you know that you have two functions that are continuous, such as f and g, so suppose f and g are both continuous at the point A, then if you add the two functions together, that's still going to be continuous. If you subtract the functions from each other, that's still continuous. If you multiply one function by a constant, that's continuous. If you multiply the two functions together, that's also going to be continuous. And then if g of a is not equal to 0, then f divided by g is also going to be continuous at a. However, if g of a was 0 at that point, we just introduced a new whole where we are dividing by 0, and so that is why it's not continuous if g of a was 0. Another useful thing is that every single polynomial is going to be continuous for any real number. You can actually extend this to the complex numbers, but most calculus classes stick with just the real numbers. And so if you see a polynomial, any polynomial is automatically going to be a continuous function. We also have rational functions. So if you remember a rational function, that is where you have a function f over a function g. So a rational function is continuous wherever it's defined, so it's continuous on the domain. And rational functions are where you have a polynomial divided by another polynomial. Some other examples of continuous functions, so we got polynomials, rational functions, we got root functions, so like the square root of something, the cube root of something, exponentials, logarithms, trig functions, inverse trig functions. All of these are going to be continuous functions on their domains. So for example, tangent, that is a trigonometric function. However, tangent has holes in its domain. So it's not going to be continuous everywhere, but it is going to be continuous on its domain. I hope this video was helpful and that you enjoyed it. Please leave a like and subscribe so that I can continue to make these sorts of videos. Please check out some of my other ones, and I hope you have a great rest of your day. Good luck with the rest of your math.